So after analyzing a structural steel beam, we will now move on designing structural steel beams. So as you all know, analysis and design are two different procedures. There are different procedure for analysis and there are different procedure for design. For analysis, usually uh, we are given a certain allowable stress as well as a certain section with an area, and then we are asked to find out the capacity or the moment capacity M with respect to steel beam. Although for the case of steel beams, instead of area, we are given a section property, which is the moment of inertia, and the section modulus and other properties related to flexure. Okay, so these are the parameters given, and this is the required for the analysis. For the design, the FY is given as well. The allowable stress the allowable stress is given as well as the given demand or the moment that must be the basis of the design. And what we are asked is to find a section with a particular section modulus or moment of inertia, because the two parameters or quantities are related to each other. So we are asked a section modulus or moment of inertia that will produce a stress less than the stress being induced by the given demand. Okay, so for the design, these are the given and this is the required. For analysis, this is the given, so I'll just change this to section modulus for consistency. For analysis, these are the given and this is the required. For design, these are the given and this is the required. Okay, so a while ago we discussed about analysis and we are tasked to find out this, the moment capacity. For design, which is the topic for this part, we will be given a given demand as well as allowable stress, and then we will be just finding a particular steel section that has a section modulus that will produce a stress that will be not exceeding the allowable stress allowed by the code. Okay, so that is the overview of analysis and design. So these are the steps in analysis of structural steel beams. Doubly symmetric hot rolled eye sections with compact webs bent about its major or strong axis. Okay. Actually, this is not analysis but design. So this must be design. So this is how you design a structural steel beam. So first, you have to take note of the given data as well as the design philosophy, whether LRFD or ASD is being asked to be used. Okay. All right. Also, some assumptions that need to be made. Assume that the hot rolled eye-shaped compact section with compact web and flanges is to be used for the design. Assume also that lateral torsional buckling is not critical. So you are already assuming some things here. You are already assuming that the W section or the steel section that you will use is limited to hot rolled I-shaped compact section. Okay. And then we are also assuming that the lateral torsional buckling is not critical. Therefore, we don't need to check anymore for the design part, the lateral torsional buckling. Although for the analysis, we have to check as well the lateral torsional buckling. If for dead loads, beam weight is not yet included, assume a beam weight based on the design requirements using the data from ASEP Steel Handbook as reference. If no design requirements can be used for assuming beam weight, the heaviest beam weight of among the type of section to be used for design may be assumed. So for designing, we still have no cross section at hand. Therefore, we still cannot compute for the beam weight or for the weight of this particular steel section. But we need to consider that weight. So just to consider that weight of the steel section that we that we are designing, we can assume some arbitrary weight based on the design requirements. Okay, using the data from ASEP Steel Handbook. Okay, but if there is no design requirements mentioned, we can assume a beam weight equal to the heaviest beam weight among the type of section enumerated or used for the design. Okay, so we can just assume a beam weight equal to the largest beam weight that you can see on the steel handbook, since we just have to have a initial section for the computation of the beam weight. Okay, because again, design is actually an iterative process. You cannot have a final design using one iteration only. So you must have several iterations of trial and error for you to have a final design. Okay, so just to be able to start the design process, the iterative process, you just have to, you must have an initial section for the beam weight consideration. Okay, take note also of deflection requirements given, if there are any. If there are no given specific deflection requirements, but the kind and or function of the beam to be designed is given, use either the traditional criteria or the maximum deflection limits from IBC, whichever is more applicable. So you also have to check, you also have to consider deflection on your design. You have to find a steel section that will that will result to a deflection that will not exceed the allowable deflection specified by the traditional criteria or the IBC maximum deflections. Okay. After that, calculate the demand due to the loads, either PU or why is it PU? It must be MU. MU for LRFD and this is MA for AST. So you have to, since we are designing flexural members, so this must be MU with respect to moment and this must be with respect to moment as well. So for the case of LRFT, MU will come from WU, which is the ultimate load combo, you the combination which uses load factors. MA is just equal to the service loads, the loads that don't use load factors. Okay, and then after that, you can use the same formula as we have used on the analysis and find the required nominal moment capacity due to the given demand or MU or MA. Okay, since phi is usually given, you can assume phi that we will use, as well as MU. MU is will be given from the given problem. So all we need to compute here is the MN, the nominal moment capacity. You will have to find a section that will produce a nominal moment capacity that is equal or greater than MU here when multiplied by the strike reduction factor or divided by the safety factor here. Okay, and then after that, determine the required design parameters of the beam section as follows. So since you already computed the MN from here, you can just divide that to Fy to compute the required plastic section modulus. Since we know that the nominal capacity with respect to yielding is just equal to the plastic moment, which is just equal to the product of Fy and Z. Okay, so dividing both sides by Fy, cancel here. Therefore, Z is just equal to MP over Fy, which is similar to this formula. Okay, so with that given beam section parameter, you can go to the steel handbook to find a steel section that has a plastic section modulus equal to or greater than this given section modulus here, plastic section modulus or plastic modulus. Okay. If there are deflection requirements, determine the minimum required moment of inertia, Ix required, if IBC deflection limits are used, or minimum required cross-section depth, D required, if traditional criteria are used. For calculating Ix, only service load combination should be used regardless of the design philosophy in use. So if there are deflection requirements, in addition to this Z, you also have to compute for the minimum moment of inertia if the deflection requirements is referred to IBC, or if the deflection requirements are referred to the traditional criteria. You have to check for the minimum section depth D. Okay, so those are just the additional parameters that you will check that must be that must possess by the steel section that you will choose, in addition to the section modulus or the plastic modulus that you will be computing here. Okay, so you will have to check the list of steel sections from the handbook and choose a section that has a section modulus greater than or equal to this, as well as a moment of inertia equal to or greater than here, or effective or total depth equal to or greater than here. Okay, so those are just the parameters that your steel section must have. Okay, so after that, uh, after you have computed these parameters, you have to select a hot rolled eye section from ASEP Steel Handbook such that its plastic modulus is equal to or greater than the Z here, just like what I have mentioned a while ago, and either its minimum required moment of inertia is at least equal to or greater than Ix, or its minimum required cross-section depth is at least equal to or greater than the D required, as I mentioned a while ago. Okay. After selecting a trial section, check the total dead load considering the linear weight of the selected trial section and compare it with the assumed beam weight. If the selected section has lighter linear weight than assumed, then the trial section may now be reanalyzed. Otherwise, if there is not much difference between them, i.e. less than 10% difference, then the trial section may still be reanalyzed. Okay? So after having a steel section that satisfies the requirement of plastic modulus as well as moment of inertia, or the total depth, you have to check the given weight of that particular section that you have chosen and compare it to the initial weight that you have assumed. Okay, so if there are no significant difference, therefore you can already reanalyze this steel section that you have chosen. But if the total weight of the section that you have chosen is greater than your assumed beam weight, therefore there is something wrong with your design, so you have to redesign. So you have to repeat the design process. Okay. So after having a still section, you have to reanalyze the section. You have to verify the assumptions made. If some of these assumptions do not hold true, it would be all right since the selected section will still be checked if it is adequate. If it passes, then that would be the design section. Otherwise, select another section. Use the concept of demand capacity ratio from illustrative example 3.5 to assess the efficiency of the section design. So as part of the design process, guys, the analysis is actually a part of the design process. After you have designed, after you have chosen a particular steel section like W16, you have to still reanalyze it. You have to compute its corresponding capacity and compare it to the given demand MU. Okay, so the moment capacity, the nominal moment capacity of the section that you have chosen must be greater than the given demand. After you multiplied it, obviously, by the strength reduction factor or the reciprocal of the safety factor. Okay, so if ever it will not be greater than the given demand, therefore you have to choose another steel section until such time that it will satisfy the requirement that the capacity Mn multiplied by the phi or the 1 over omega must be greater than or equal to the given demand Mu. Okay? And then check the other assumptions made. Check whether the section is not really critical with respect to lateral torsional buckling, etc. Okay? And you can also check the efficiency of your design. So after you have computed Mn, you can multiply it to phi and then divide it by the given Mu. So as you can remember, that is actually the demand capacity ratio. So as much as possible, the ideal is that the demand capacity ratio is equal to 1. Okay? Or at least near 1. Okay? Near but will not exceed 1. Okay? Because if the demand capacity ratio exceeds 1, It just means that, I'm sorry, this must be ano, ah, interchange. Baliktad, baliktad. Dapat, ah, burahin ko na lang. Dapat baliktad yung ano ko, yung pagkakasulat. Dapat, MU over PMN. So that is the demand capacity ratio. Kasi nga, demand capacity ratio. So dapat, demand yung nasa taas, tapos yung capacity yung nasa ilalim. Okay? So, ideally, we want the demand capacity ratio to be equal to 1. Meaning, the MU is just equal to the VMN. Okay? The demand is just equal to the capacity. Okay? Because if this is 1, if you multiply this to the right side of the equation, the resulting equation is just equal to MU equal to VMN. Okay? We want that to happen. We want our design capacity ratio to be as much as 1, but not greater than 1. Because if ever the demand capacity ratio is greater than 1, it just means that the numerator is already larger than the denominator. If the demand capacity is less than 1, therefore, we can see that the numerator is less than the denominator, meaning the demand is less than the capacity, which is something that we want. We want the demand to be always less than the capacity. Okay? As much as equal. But we don't want our demand to be greater than the capacity because it will result to failure. Okay, so that technically that is just the different procedure that you have to undertake whenever you design structural steel beams. So just to give you an experience on designing a structural steel beam, we can just solve this sample problem. The question asks us to select the best hot roll W18 section, which is made up of A36, ASTM A36 with Fy equal to 250 megapascal, that should be used for the design of a 6-meter simply supported floor beams. The beam is supported to carry uh, a superimposed dead load of 15 kilonewton per meter and live load of 30 kilonewton per meter. Both uniform loads applied throughout the span. The beam is laterally supported at its 4 points and at its supports. Use a lot of this specification. So according to the problem, we have a simply supported beam like this one, made up of W18 section. Okay, so meaning the depth is at least 18 inches. Okay, if we will, meaning if we will try to select a wide flange section, we have to make sure that the depth is 18 inches or more. 18 inches or more. Okay, if this is the I section, if this is the I section. Okay, so it is made up of ASTM A36, meaning its Fy is equal to 250 megapascal, and then its length is 6 meters, according to the problem. Uh, it is loaded by a uniformly distributed load coming from a dead load equal to uh, 15 kilonewton per meter and a live load equal to 13 kilonewton per meter. So you have to take note that the given loads, the dead load and the live loads are actually superimposed. So when we say superimpose, it means that we just impose the loads obviously on the beam. Baga pinatong lang siya. Meaning hindi pa kasali dyan yung self-weight ng beam itself. Okay, so you have to consider the self-weight of the beam separately. Okay, so they are uniformly distributed load applied all throughout the length of the beam. The beam is laterally supported at its 4 points as well as at its support. So there you have lateral bracing here at its end points as well as every 4 points. So meaning you have lateral support here, here, and here as well at every 4 points. Meaning you just have to divide the whole span uh, uh, into 4 equal parts. So you have lateral bracing here, 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 and here. Okay, according to the problem. So the unbraced length is just equal to 6 over 4, okay, meters. That is the equal unbraced length all throughout the length of the beam. So we have to find a steel section, which is a W18 steel section that can withstand the given demand with respect to the different checking that we have to do with respect to flexure, with respect to shear, and with respect to deflection. So we have to find a section that will be able to withstand the flexural capacity, the shear capacity, as well as the deflection capacity. Okay. So rewriting the given data, the length is 6 meters, dead load, live load, and then we have to choose W18. And then we can assume a beam weight equal to 463 kilogram per meter since it is the heaviest among the W18 sections. So if you will try to look on the Asep Steel Handbook, you can see there the series of W18 sections. If you will try to look the heaviest weight of W18, you can see that the heaviest is actually 463 kilogram per meter. So you can use that as your initial beam weight. Okay. The beam is laterally supported at 4 points. Every L over 4 and RFD specifications are being used. So you can assume first that the section to be selected for design is compact for simplicity of design. Okay. So we can assume that the section, which is this, is compact, meaning its flanges as well as web are compact. Okay. Assume also that the lateral torsional buckling limit state is not critical, meaning it doesn't have a tendency to exceed its yield stress or yield strength with respect to lateral torsional buckling. So for the computation of the given demand induced by different loads here that are mentioned on the problem, since we since we are tasked to use load combinations, I mean, since we are tasked to use LRFD design philosophy, we have to use load combinations that uses load combinations that use load factors. Okay, so for the case of LRFD, there are actually many load combinations of load, dead load, live load, wind load, or quick load. So since we are just dealing with dead load and live load, the load combination that we will just consider is the first one, the first load combination, which is equal to 1.4 dead load, and the second one, which is equal to 1.4 1.2 dead load plus 1.6 live load. Okay, and then we just have to choose the most critical demand, the largest demand that we expect that our beam will carry. So if you will just try to substitute the magnitude of dead loads and live loads, uh, we can compute for these ultimate loads. So again, you have to take note that for the case of the dead loads, you have to consider the weight of the beam. Okay. So we have considered the weight of the beam and then added it to the superimpose. So that will be the total dead load that you will have to substitute on these load combinations. Okay, so you can see here the load combination that will result to the most critical load is the second one, the 1.2 dead load plus 1.6 live load, which is usually the load combination that governs for cases wherein the loads that we consider are just only dead loads and live loads. Okay, so we have to choose a steel section that will be able to withstand the effect of a uniformly distributed load equal to 71.45. Okay, so let's start the checking with respect to lecture. So let's check the maximum bending moment that can be induced by a 71.45 uniformly distributed load. So for a simple supported beam, usually the maximum moment occurs at the midspan, which is equal to WL squared over 8. So since W is already computed and we know L, so we just have to square it and divide it by 8. The result is equal to this. Okay, so meaning the load here will induce a maximum ultimate moment. This ultimate load will induce a maximum moment on the simply supported beam equal to 321.53. Okay, so based on that ultimate moment or maximum moment, using this formula for LRFD, we can compute for MN. since we know the value of phi for flexure, which is equal to 0.9. Okay, so computing Mn, we can see that Mn is equal to 357. So we have to find a steel section that has a nominal moment capacity equal to 357.252. Okay, although that is not usually the direct parameter that we use as a basis for choosing a section. So we usually find a section modulus that will satisfy that given nominal moment capacity. Okay, so since we know that the nominal moment capacity for yielding is just equal to the plastic moment, which is just equal to the product of Fy and Z, so we can compute for Z, since we know Fy as well as MP, which is just equal to Mn, which is the value that we have computed a while ago. Okay, so substituting to the formula, we can compute for Z, the plastic modulus, which is equal to this. Therefore, if ever we will choose a W18 section, we must choose a W18 section that has a plastic modulus equal to or greater than 1429 mm cube. Okay, so that is the first basis of our design, the plastic modulus. Okay, so since there are deflection limitations that was mentioned, is there a deflection limitation? May I just reread the problem? I think there is no deflection limitation. There's no deflection limitation, but we usually check that as well. Okay, so just to give you an experience on designing a beam considering deflection, we can just use the deflection limitations from IBC. Okay, so we will just find a section property of this steel section that will produce a deflection that will not exceed the given deflection limitation from ABC. Okay, so for floor beams, since we are talking about a beam here, use IBC limits, IBC deflection limits to determine the required minimum moment of inertia. IBC requirements for floor beams are as follows. Maximum live load deflection is equal to 1 over 36, 1 over 360, 1 over 360 of the span length, and maximum dead and live load deflection is equal to 1 over 2 of the span length. For deflections, service loads must be used. You have to remember that. Okay. For deflection calculation, we are just using service loads. We are not using factored loads, loads that are multiplied by load factors. We are just using the dead load and live load alone without using any load factor for the computation of dead load. Because we are concerned with the deflection induced by dead load and live load, not their worst case scenario. Okay. So for a simply supported beam with uniform loads, the formula for computation of the maximum deflection that occurs at the midspan is equal to this. So in accordance to the IBC deflection, if we will try to check the corresponding deflection induced by the live load alone, according to IBC limitations, it must not exceed L over 360, which is equal to 16.67. Okay. Therefore, we have to choose a steel section that has a moment of inertia that will produce a deflection equal to or less than this deflection limitation from IBC code. Okay, so substituting every term here, substituting W, L, E, as well as the delta max so that we have computed here, we can find for the required moment of inertia, which is equal to this. Therefore, in addition to this parameter, we must also use this parameter for us to be able to properly choose a W18 section that can withstand the given limitation of the problem. Okay, but you have to take note that is just for live load deflection. For the combination of dead and live load, the deflection that they will induce together, according to the code, must not exceed L over 240, which is equal to 25 mm. So we have to find a moment of inertia that will produce a deflection equal to or less than 25 mm. So again, substituting everything on the formula, the W, the L, the delta that we have computed here, and then the E. Therefore, we can compute for the moment of inertia. And again, you just have to realize that the W is just equal to dead load plus live load. We just use the service loads for the computation of dead loads. We don't multiply them with a certain load factor. Okay, so the corresponding moment of inertia requirement for the steel beam to not exceed the maximum deflection allowed by IBC code, which is equal to, or IBC limitation, which is equal to this, must be equal to or greater than 167. Okay, so therefore, in order for us to ensure that the steel beam will have a deflection that will not exceed 25 mm, therefore its moment of inertia must be equal to or greater than 167. Okay, so with this, using these two moment of inertia requirements, if we will try to choose which of these two moment of inertia will govern, obviously, we will choose the larger demand. Okay, this is the larger restriction. Okay, on the moment of inertia. Okay, because the formula here is actually greater than or equal, greater than or equal. So meaning the moment of inertia that will satisfy this deflection limitation must be equal to this or greater than. And then for this particular limitation, for this particular deflection requirement of the IBC deflection limits, the minimum the minimum moment of inertia must be equal to this. So in order to satisfy both cases, we 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 have to use this. Okay, because it says that the moment of inertia must be equal to or greater than this. If we will choose this, it will not satisfy this requirement because obviously 151 is not greater than 167. But if we will use this requirement, it will satisfy both cases because obviously 167 is greater than 151, which is the requirement here. Okay, so we have to choose Ix required equal to 167. So we have now two bases for choosing a steel section, the plastic modulus as well as the moment of inertia. Okay, so using those bases, we can select a trial W section such that it fulfills both minimum required plastic modulus as well as the moment of inertia. Okay, so the trial section that we have chosen is the W18 by 46. So you can obtain its section properties from 2004 ASEP Steel Handbook. Okay, so since the selected trial section is lighter than the assumed, so this the corresponding weight of this W18 by 46 is just equal to 68 kilogram per meter, which is lighter than the assumed weight. We assume the weight of the beam is equal to 463, which is very large actually. So since we assume a weight equal to 463, therefore since the true weight of the steel beam is not actually 463, therefore you can expect that the given loads will actually produce a moment lesser than what we have computed a while ago. Okay. Since the total weight here is not actually as high as 463, but only 68. Okay, so you can expect the moment demand here that we will compute, if ever we will try to change this to 68, will be lesser than the one that we have already considered here. Therefore, the trial section is very safe. Okay, it's already very safe because it assumes already that that its weight is actually 463, even though it is not actually 463 kilogram per meter. So so the design is actually safe. So because you expected the worst case scenario, okay, of having a very heavy beam. Okay, since the trial section is lighter, we can already reanalyze or analyze. We can already analyze the given beam, so we can just find its capacity, the capacity of a W18 by 46. So you can just repeat the procedure that we have done on the previous topic, the analysis of beams. You can just repeat the procedures there and analyze the trial section, the W18 by 46. Analyze it and then find its nominal moment capacity and then multiply it to phi and then compare it to mu that we have computed a while ago, so that this product must be greater than mu or equal at least. Okay. So if ever you will see that moment capacity of a W18 by 46 section is actually larger than the demand, the MU that we have computed here, which is equal to 321.53. Therefore, the trial section is actually okay and safe. Okay. Therefore, we can expect that the trial section can easily withstand the stresses that will be induced by a magnitude of MU equal to 321.3. Okay. So for the analysis of a W18 by 46, this is already skipped on this particular example. So that is already left as an exercise for the students. Okay. So you can just refer to illustrative example 4.4 for reference for the analysis. Okay. So upon verifications, the assumptions used in this problem are true. So okay yung mga in-assume natin kanina. The section is compact considering flexure. You can actually check this for compactness. And if ever you will check that, you can see that the section is really compact, which is what we have assumed in the first place. Okay, so check tayo dyan sa assumption na yun. The lateral torsional buckling is not critical. LB is equal to 1.5, LB is equal to 1.631. Therefore, LB is less than LP. Okay, so if ever we will also check the lateral torsional buckling, you can see that the LB, which is equal to 6 over 4 or 3 halves or 1.5, is actually less than LP, which is the limiting unbraced length for uh, for the non-criticality of lateral torsional buckling. If you will try to remember the graph, always remember this graph on your mind to help you on uh, on uh, on the lateral torsional buckling cases, wherein the x-axis is the lateral unbraced length, and the y-axis is the moment capacity. So you can see here that there are several limitations here. The first limitation is LP and the second is LR. So for the first limitation, wherein this highest magnitude of moment here is equal to MP, the plastic moment, we can ensure that the beam will experience a maximum moment equal to plastic moment if the unbraced length is equal to LP or less than. Okay, or in other words, if the unbraced length will be within this region. Okay, since the LP is equal to 1.631 and LB is less than 1.631, therefore, we can say that the unbraced length falls within this region. Therefore, lateral torsional buckling is actually not critical. Okay, so therefore, the assumptions that we have mentioned on the first part of the solution is actually true. Okay, meaning lateral torsional buckling is not actually critical. Okay, the design moment strength of the beam with trial section is 371.5 kilonewton meter. So if ever you will try to compute for the VMN of this W section, you can see that its moment capacity is equal to 371.5, which is larger than the given demand, which is equal to 321.53. So therefore, uh, the section is okay with respect to flexure. Okay, with respect to flexure only. So as you can remember, we have to check it as well with shear. Okay, as well as deflection, although we already considered deflection here on this part. So all there's left to do is the checking with respect to shear. So upon checking, shear is also not critical. Okay, so therefore, W18 may be used as the section that can withstand the given demand of dead load, superimposed dead load equal to 15 and live load equal to 30 kilonewton per meter. Meaning, if we will impose a load, dead load, superimposed dead load equal to 15 and live load equal to 30 kilonewton per meter on this simply supported beam, we can assure that the maximum bending moment that will that will be produced by those superimposed loads will not exceed the moment capacity of the section here, which is equal to 371.5. Simply because we have already computed that uh, the, the, the maximum moment that they can induce, assuming that the weight of the beam is actually as large as 463, is just equal to 321. But since the weight of the steel beam is actually less than 463, therefore you can expect that the actual demand is actually less than 321. So maybe it's just 300 or 280, which is way less than the capacity of the W18 by 46. Therefore, the trial section that we have chosen is actually safe. That is the the main purpose of designing. You have to ensure that the section is actually safe if ever you will check every limit state or every design check that you have to undergone. Okay, so as long as the design is safe, as long as the stresses are not exceeded, allowable stresses are not exceeded, as long as the allowable stresses as well as the deflections are not exceeded, therefore your design can be accepted as safe. Okay, so therefore what I'm pointing out here is there is no actually specific design. Okay, the design is actually based on the designer. Okay, so the only basis there is as long as their design will result to a safe design, meaning if you will try to check the induced stresses or the deflection from the design that you have chosen, as long as they will result to safety or safe stresses, safe magnitude of stresses as well as deflection, therefore we can still accept your design. Okay, even if you have chosen a different steel section here, let's say for example a W18 by 40 only, as long as you can show that the flexure capacity as well as the shear and deflection limits are met, therefore I can accept or we can accept your design as long as you can prove that your design is actually safe and okay. Okay, so we just have a final note here. Note, as for the assumptions, if they are verified that they do not hold true, there should still be no worry, since the most important thing is that the selected section is adequately designed. Therefore, even if lateral torsional buckling should be considered and or the selected section is not compact, it does not mean that they are not adequate anymore. So, yun na nga yung most important part naman ng designing. Kasabi ko lang, di ba? As long as you can show proof or show proofs that your design is safe, therefore, we can still accept your design. As long as there are proofs that the design is safe. As long as you can show that the flexure as well as the shear and deflections requirements of the code are met, therefore, we can still consider your design. Okay. But if ever there is a scenario wherein we have seen that that your design, the section that you have chosen, actually fails with respect to, say, for example, shear or deflection. Therefore, we cannot accept your design. You have to redesign your work. You have to choose another steel section that will result to a safe section with respect to flexure, shear, as well as the deflection limitations. So that is how you design structural steel beams, specifically flexural members.